Quantum mechanics is perhaps the most successful scientific theory ever formulated. It is the foundation of physics, chemistry, and biology. You could say everything flows from quantum mechanics. And yet one of the world's greatest experts on quantum theory once said, "I think I can safely say that nobody understands quantum mechanics." He included himself.
We see things in particular places and times. Nothing could be more straightforward. Classical physics is built on those concepts, and atomism, Newton's theory of gravity, classical mechanics. But it doesn't seem to be built into quantum mechanics. Something very different is happening there.
And that's part of why we think that quantum mechanics is true.
At the heart of quantum mechanics is the idea of the superposition principle. So that, for example, when we describe an electron in space, the electron, in a sense, can be in various places at once. It's in a superposition of being here, 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 and here. We describe it by a wave function, which is something that's really sort of spread out in space. It's rather like a field in space.
The mathematical equation that describes the wave function was written by Erwin Schrödinger in 1926. It enables us to calculate the probability of a quantum particle being in a particular position or state extremely accurately.
Schrödinger thought of entities as being spread out in space. He spoke of waves of matter. And like any wave, there's an amplitude, and all of that goes into the mathematics of his equation. The extraordinary thing about this is that whenever you do a measurement, you don't see the wave as something spread out. It seems to collapse onto something point-like.
The widely accepted explanation for many years emerged from the Niels Bohr Institute in Copenhagen. Niels Bohr was one of the founding fathers of quantum mechanics.
In the Copenhagen interpretation, the key idea is the act of observation or measurement. There is no quantum reality except relative to a measurement, and that is always to be described in classical concepts. The act of observation or measurement induces the collapse of the state.
For physicists such as Einstein, Schrödinger, de Broglie and others who had created quantum mechanics, this explanation was absurd. Schrödinger came up with his now famous thought experiment to explain why. If you shut a cat in a box along with something that could kill the cat, depending on a radioactive decay, then does the cat count as an observer? Or is the cat either alive or dead only when we open the box and look inside? Einstein expressed his disbelief in the Copenhagen interpretation by asking, "Do you really believe the moon is not there when you're not looking at it?"
It's just completely implausible that the universe cares whether a human being is doing a measurement or not. It can't be that the universe obeys different physical laws when a measurement's happening from when it isn't.
I said when measurements are performed. This is our way of interacting with the microscopic. So it's for this reason that it's called the measurement problem. But it's much more than that. It's a fundamental conceptual question about what on earth is going on in reality, in the interaction between micro and macro.
Niels Bohr and the Copenhagen interpretation presented a kind of view to work with, which was that you didn't really take the Schrödinger equation as a serious description of the world. It was just a way of making calculations. And it wasn't really giving you a picture of what's going on in the world. Whereas we do want a picture.
Like, how do you go from these wave functions to the actual things of the world that we see, which are chairs, shoes, trousers, air, particles, stuff? And that's a measurement problem. How do you go from one to the other? And it opens a can of worms.
The fundamental principles of quantum mechanics, the Schrödinger equation, were originally applied very successfully to microsystems, systems at the level of atoms, molecules, and even smaller. But of course, then the question is, how do we describe large, everyday objects, so-called macroscopic objects, which themselves are made of atoms and molecules?
The Copenhagen interpretation left physicists and philosophers with many unanswered questions.
No, there's no proof of that.
Gradually, other theories and solutions to the measurement problem began to emerge. One theory, based on ideas proposed by Louis de Broglie in the 1920s, was put forward by David Bohm in 1952. Bohm's approach is an example of a hidden variables theory.
One sort of attempt to resolve these conundrums was to introduce new entities into the mathematical formalism, and those new, we call them degrees of freedom, those were going to pick out the cat alive or the cat dead, one or the other. The difficulty with this is that it doesn't seem to be possible to include photons and other relativistic particles in the same way. If you try to do so, well, there's been no agreement on how to go about it. For 70 years now, there's been no agreement on how to extend the theory to deal with radiation as well as matter.
In the 1980s, new equations were formulated to support new dynamical collapse theories. They said that when enough particles are involved, the wave function collapses at the macroscopic level of its own accord.
But the more we know about the Schrödinger equation, the more we can see that it really is very precisely the evolution of a small system. The thing is that true of things when they get big? And my own view is that it's not true of things that get big, or more accurately, it's that small things will preserve their superpositions for a long time. But big things, certainly as the size of a cat, this superposition will instantly, almost instantly, become one or the other. And that this happens spontaneously. It's nothing to do with anybody coming looking at it. It's the way the world operates. Well, it's not that there's a difference between large level and small level, in my view. It's that the large level, the one or the other happens very fast. Small level, one or the other happens very slowly. And that's all it is.
So there are dynamical models that can achieve the separation of fast and slow degrees of freedom. They can be applied to certain systems, but not to photons, not to relativistic particles. So the dynamical collapse theories are in the same boat as the hidden variable theories. They don't actually succeed in describing real-life experiments that do involve photons.
Another solution to the measurement problem was put forward in 1996 by Carlo Rovelli. It does away with the wave function almost entirely.
The relational interpretation of quantum mechanics can be traced to the very first intuition of Heisenberg when he first discovered quantum mechanics. Heisenberg himself tells a story of how the idea of quantum mechanics came to his mind. He used to walk in the park and he sees a man walking. But he doesn't actually see the man walking because it's very dark and there are always some lamps. So the only thing he sees is the man appearing under a lamp, disappearing, and then reappearing under a lamp, disappearing, and reappearing again. And he has this flash and says, what do you know about an electron? And maybe it's just flashes of appearance here and there and nothing in between. Heisenberg realized that to understand the atomic world, we should think of particles something happening here and here and here. So a particle is a sequence of events. Particle hitting this, hitting there. There's no wave function. Wave function is just our way of computing things. When the particle interacts with something, it exists with respect to this object. So things get a reality for us when they interact with us.
The difficulty with the relational interpretation is what happens to all of the atoms that don't interact with us. Do they not exist and they come into existence on interacting with us? It's reminiscent of the Copenhagen interpretation. There is no quantum reality unless in the context of a measurement. There may be ways of improving on this, absolutely, but it's, again, work in progress.
Simon Saunders was a young professor at Harvard University in the early 1990s.
In my early days at Harvard and before that in my PhD thesis, it was obvious to me that the difficulties of hidden variables and dynamical collapse, and including relativity, were enormous, formidable. And the Copenhagen as an interpretation of the theory was incoherent. So I looked elsewhere and I was led to the ideas of Hugh Everett.
Hugh Everett was a graduate student at Princeton University when in 1957 he came up with a startling new way to approach the measurement problem.
Everett put forward the proposition that Newton's laws hold at all times, laws of electromagnetism hold at all times. Why shouldn't the Schrödinger equation hold at all times? One would think that if it's a law. But the trouble with that, of course, is you're led to Schrödinger's cat, the cat superposed live and dead. But Everett was ready to bite that bullet. What if that was really happening? But these ideas were difficult. They sounded mad. They were treated as fantasy. No one took them seriously, especially in philosophy.
The Everett interpretation was not even on the table in those days. We didn't discuss it. The major figures in philosophy departments who were working on foundations of quantum mechanics essentially overlooked Everett. It was considered too bizarre, I think.
To my view, the many worlds, or the Everett interpretation, if you like, is a reductio ad absurdum. And so if you believe in the Schrödinger equation, then you would get this absurdity of a dead and alive cat simultaneously. Now the question is, why don't we see that?
So I looked for ways to introduce the ideas that were not immediately overwhelming. I did suffer from it, there's no doubt about it, and I was an untenured professor and so forth. It was a bit damaging. But by the mid-90s, Oxford took a look at me and they were ready to take the risk. They said, come to Oxford. And that was the real beginning of it all.
Moving to Oxford University in 1996, Simon found other physicists and philosophers who were ready to take another look at Everett's approach.
Simon Saunders nearly single-handedly brought the Everett interpretation to the fore in philosophy of physics.
Across the board in the Everett interpretation. So it is very much the interpretation as set out in these two books.
Simon's work here was both intellectually very important and I think actually personally very courageous, because that was a time where in philosophy, if not in physics, these ideas were not really taken very seriously, and there was a certain amount of risk, I think, in working in these areas.
What was really wonderful was encountering young people, undergraduates even, who really lit up on these ideas and went places I had not envisaged, went to new ideas altogether.
The way that I was understanding you when I was reading your paper is we should really justify...
This is actually picking up on something Simon said.
David Wallace, above all, initially is my graduate student and PhD student, but I'm not sure who learnt more from whom, went on to write what is now, I think, the definitive book on the Everett interpretation, The Emergent Multiverse. I just want to say that that's what I meant.
Everett's theory, in many ways, is very simple and very conservative. It just says scientific theories give us a literal description of the world, and quantum mechanics is literally and exactly true. Before Everett, the assumption about the Schrödinger cat was, well, a cat couldn't be alive and dead at the same time. We don't see cats alive and dead at the same time. So either Schrödinger's cat makes no sense, or at least the theory can't predict that. If the theory predicts that, the theory must be wrong. Everett said, in effect, well, what would it look like if a cat was alive and dead at the same time? And the answer is that because humans looking at the cat are just one more measuring system, what it would be like for me to see a cat alive and dead at the same time, it wouldn't be like seeing double or being drunk or something like that, which is often what you imagine. It would be that I would end up doing two things at the same time. So instead of just being cat alive and dead at the same time, there's now cat alive, David sees living cat, and cat dead, David sees dead cat at the same time. And so reality is just splitting into these sort of parallel streams. There's a live cat stream and a dead cat stream, and they're both going on at the same time, but from the point of view of someone inside one of the streams, everything looks perfectly normal.
Simon and his circle of colleagues became known as the Oxford Group, as together they addressed problems that had long been thought to undermine the Everett interpretation.
Many things were left incomplete in Everett's work. There were lots of open questions. Everett himself left the field immediately on finishing his thesis. He never wrote on quantum mechanics again. He was discouraged at the reception of his ideas.
Two traditional stumbling blocks, technical difficulties, or theoretical difficulties for the Everett interpretation are, on the one hand, the question of whether and how a plurality of determinate realities emerges, and the other one is the problem of probability.
And so the question arose in the case of the Everett interpretation, what are these branches that are emerging out of this measurement process? The solution wasn't really provided, I think, until essentially Simon Saunders' work in the late 1980s.
Independent of decoherence, we have the simple sum that all of the fine-grained history
He was the first to realize that
consistent with the coarse-grained history.
the process of decoherence, which had at the same time was being understood within the physics community in more and more detail and more clarity, it itself provided the basis of a unique way of looking at the superposition principle. In other words, it provided a unique account of how these branches were described within the theory. And this was, again, picked up and further clarified by David Wallace in his work. So the role of decoherence in making precise the nature of the branches in the Everett picture was really, I think, largely developed by the Oxford group.
Think of ripples in water, still water. Think of how they can interfere with one another, cancel out and reinforce. Now think of turbulence, white water. Can you have ripples in white water? No. This is decoherence. The cancelling out of any possibility of interference. Now think of a heavy atom. And think of it in a radiation bath, just thermal radiation. That heavy molecule will interact with certain photons, and there will be a very complex system of correlations of that molecule with the photons. If that molecule became a superposition, a molecule here and a molecule there, the state of the molecule here will also get correlated with all of the photons. Now, the overall state of this molecule correlated with all the photons, and this state of the molecule correlated with all the photons, they're not going to be able to interfere with one another. It's white water. It just won't happen. This is decoherence. And in effect, they've become autonomous, independent little worlds.
What decoherence theory taught us was that this constant branching is something that's happening naturally, just as a result of physical processes all the time. So if I had a large particle going through the air in this room, its position would be being decohered by the air because millions of collisions with air molecules are constantly recording in the microscopic state of the air in the room, just where the particle is.
Decoherence theory, it gives the general theory of branching. And here's the thing, if you follow a branch, these branches are defined in terms of dynamical variables taking on certain values. And you get equations for the branch. And those equations are the classical equations that we know and love. So classical mechanics, Newtonian gravity, comes out as the laws or the equations governing the branches. But the beautiful thing is this is all following from the Schrödinger equation. So this is an amazing achievement of the Everett interpretation in that it allows us to see these forms of matter, I called them, the kinds of equations that they follow. It allows us to see how these come out of the formalism of quantum mechanics.
The implications are astonishing. Each branching brings a new, completely separate world into existence, containing all these forms of matter, just like the world we see. Decoherence theory tells us that because branching is happening all the time on a vast scale, unimaginable numbers of parallel worlds are being created all the time. We can't see them, we can't interact with them directly, but according to the equations, they must be there.
Now the question is, before the branching occurs, what probability do you give to the outcomes in each of these branches? How do you assign a probability to a process in which everything that can happen does happen? What does it even mean? And this is a stumbling block for many, many people. Even if they come to terms with the extraordinary, extravagant ontological nature of the branching process, they find it very difficult understanding probability in this theory.
Quantum mechanics is supposed to be a theory that issues predictions in terms of probabilities. So if you've got now a reinterpretation of quantum mechanics which says there are no probabilities, then you don't have any predictions anymore, so you don't have a scientific theory, so the whole thing's a big mess.
Quantum mechanics, as we use it in the lab, is a probability theory. It says that a given thing happens 32% of the time. We test that by doing an experiment 100 million times and seeing if we get 32 million copies of the result. It's difficult to understand how to grasp that if the world isn't doing one thing or another, but is constantly branching so that everything happens in some branch.
In '99, David Deutsch published a paper where he said, hey, let's think of probability in a many-world setting in terms of decision theory, because determinism or no determinism, you still have agents living in this world, and these agents still need to make choices, including in situations where one thing's going to happen to them if the experiment has the outcome A, and a different thing's going to happen to them if the experiment has an outcome B. So Deutsch suggested that maybe something like probability enters into the formula by which rational agents make those kinds of decisions. And that was the key for me. That seemed to be a thing that could perfectly well make sense even in a fully deterministic context.
Decision theory usually operates in the face of uncertainty. But can there be uncertainty when all the outcomes of an experiment actually happen? Is uncertainty really needed?
You're warned there's going to be a flood. What credence do you give that warning? If you give it high credence, you'd better prepare for the flood. Somebody else tells you there's going to be a drought. What credence do you give that? If you give it high credence, you'd better prepare for a drought. So you sort of have to prepare for both, depending on your credence in each. In a one-world theory, the only basis why you would do that is because you don't know which of them takes place. But in the many-worlds case, you know they will both take place. It's exactly the knowledge that they both take place that forces you in the same juggling act, preparing for the drought, preparing for the flood, that you would normally have to go through in a one-world theory when you didn't know which of the outcomes obtains. If only one of them is real, we don't know which. Then we'd reason under uncertainty, lack of knowledge. But if we know they all occur, we still go through the same cognitive engagement of credence. What weight, what seriousness, how do I apportion present resources?
Following David Deutsch, David Wallace showed how agents who are rational should apportion their resources, just as they would using the usual probability rule of quantum mechanics. Simon Saunders has another proposal on how to make sense of probability without bringing in any subjective notions at all.
Branching is going on all the time. Decoherence theory teaches us this. So there are innumerable branches present in one outcome. They all have the same outcome. And another innumerable number of branches, they all have the other outcome. So now count those innumerable numbers, make them numerable, divide up all of the branches into equal amplitude branches. Now when you do that, and you look at the relative numbers of branches with one outcome versus the relative number with another outcome, that gives you back the probabilities.
Far from excluding probability from quantum mechanics, the Everett interpretation has a place for it in the form of both objective chance and subjective credence, and it explains how they're related. But the many worlds of the Everett interpretation leave us with profound metaphysical questions.
Right at that moment of branching, you've got all of these successors, and you might think the natural thought is, I will be one of those successors. But that actually is probably not the right way to understand this. I really am going to become them all. They are all equally me. What does it mean to think of oneself as becoming a large number of persons? What is a person? Is it something momentary, just like that? Is that what a person is? Or is it something extended in time? How big is that extent? Is it seconds? Is it minutes, hours, years? I don't want you to despair and think, oh my God, if I take the Everett interpretation seriously, I've got no idea what it means to, look forward to going for, a picnic this afternoon. So here's what it means. I will, with such and such probability, go on a picnic, 70%, and I will, with 30% probability, stay home. And that statement is exactly correct in the Everett interpretation. And what it means, 70% of my successors will go on the picnic, 30% of them will stay home. And I don't have to mention that there's millions of me's doing that thing, do you see? But it shows how we can continue to talk as we ordinarily do, consistent with the Everett interpretation. I do think that's important.
But after a century of debate and experiment, there is still no consensus about the meaning of quantum mechanics and how it represents reality, if indeed it does.
I think that the work that Simon, David Wallace and others are doing on many worlds, it's very useful because it's sort of bringing down the strangeness of quantum mechanics and forcing a lot of people to rethink the strangeness and the consequences, and in particular the consequences of taking seriously the idea of quantum state.
That I think the Everett interpretation is simply the best way we have to understand quantum theory. So the question to me is, will quantum theory be overturned in my lifetime? Will it be overturned at all? And it's true that scientific theories often change, but usually not at this scale. Quantum theory isn't simply a particular theory of physics, it's a framework in which we write physics. Effectively all physics, or virtually all physics, is quantum physics. We've only ever really had two languages in which to write physics. Until the early 20th century, we wrote physics in classical language. Since 1928, we've mostly written physics in quantum language. So the question is, will there turn out to be a new language that goes beyond the classical or quantum language in which we'll write physics? Or will it turn out that after a false start, we found the right language to do physics when we found quantum theory, and it's just the question of what we should write in that language? For what it's worth, I think my money is on the second, but who knows?
The big challenge, still outstanding, of how to marry quantum mechanics with the general theory of relativity, Einstein's theory of gravity. How do we get that engagement working properly?
I think that experiments, before too long, will start to show that there must be deviations from conventional quantum mechanics. It'll tell us that the theory of quantum mechanics, as we now know it, isn't exactly true. It will give us some better hint as to what kind of theory we must look for, which goes beyond quantum mechanics. This will be a theory which brings together quantum mechanics and Einstein's gravitational theory. I think it's going to have to involve ideas that are very different from the ones we have now. And so it will be an absolutely major revolution in the way we look at physics. But as with quantum mechanics, a lot of the clues were there already in classical mechanics. So if you look for the clues within the earlier theory, it's not that we throw all the tools out. We pick the right ones up, hone them, and develop them in different ways. And that was certainly what happened with both quantum mechanics and general relativity.
It's like, when Copernicus discovered that the Earth goes around the sun, had he got to the final truth? The world is a sun with the planets around? No, but no doubt he has understood something, right? No doubt his picture of the solar system, it's a much better insight into reality. It's a better tool for understanding reality, and that's what science does. It increases our capacity of understanding reality step by step, I would say.
Simon, you're the defender of this view. You think there really are parallel universes. Does it change how you live your life?
Well, let me say, it's not quite that I believe there are parallel universes.
I believe there are parallel cats.
One thing that I sometimes get asked is, do you really believe the Everett interpretation? That's a difficult one. I believe this is the only way to make sense of quantum mechanics from a realistic point of view. Is quantum mechanics true? That I don't know. But of course, whatever replaces quantum mechanics could be even more challenging than the Everett interpretation. We'll see. Watch this space.